Aditi, the stage is yours.
Hello, everyone. I am Aditi Kabra. I'm going to be talking about verified train controllers for the Federal Railroad Administration train kinematics model, which through the rest of the talk, I will call the FRA model. This is joint work with Stefan, Mitsch, and André Platzer, and we're all affiliated with the Computer Science Department at Carnegie Mellon University. These are trains. They transport goods and people efficiently. We like them. But it's important that they stop where they're supposed to, following these signals. Otherwise, they could collide, resulting in loss of life and property. This is the problem statement. We're designing a train controller that must stop the train by E, end of movement authority, the point. You might think this is a straightforward problem because the track is one-dimensional, the endpoint is fixed, but it's difficult because train motion is very complicated, with lots of forces interacting subtly. For example, suppose that you're going uphill. Gravity acts on the train to decrease acceleration. A slower train results in lower resistance because resistance is dependent on velocity. But decreased resistance means acceleration has increased, and a train that travels faster encounters changes in slope much faster. And this is all while air pressure brakes ramp up gradually as pressure propagates along the brake pipes in the train until saturation in a time-dependent fashion. Air brakes are a braking mechanism that are used in most freight trains, and they're a very dominant effect, but like this gradual ramp up is also significant. It takes up to 20 seconds for these these air brakes to ramp up. Further, important effects like the exact slope of the track and the exact curvature of the track aren't even known at the time when we are designing the controller. Given that this is a complicated system, it is difficult to design a controller that you are sure is correct. Controller validation using testing and simulation has the drawback that you only get to test a finite set of cases out of infinitely many possibilities. We use the complementary approach of formal verification, where you take the train controller and dynamics and express them in mathematical logic. And then you write a proof that shows that that the train is safe. We do this in computerized theorem prover, Chimera X. The advantage of using a computerized theorem prover is that the proof becomes more reliable as well as repeatable. So one verification at once covers all of the infinitely many possible cases, once and for all. This is the first work that accounts for all the effects in the FRA model. And in the process of finally overcoming all of the challenges to create a verified train controller that's realistic, we contribute generalized techniques to verified embedded system design. This slide compares a numerical integration-based controller from the literature to the formally verified model in the present work. Because train dynamics is so intricate, the numerical integration-based controller conservatively stops over 2,000 feet short of the end of movement authority. This is not very efficient. Suppose you are trying to offload goods onto a platform. This train has stopped hundreds of meters away. In contrast, our verified controller, by reasoning carefully over 180,000 proof steps, was able to reduce this gap to 502 feet. I will now talk about some of the techniques used in the paper. But before that, let me quickly introduce you to train dynamics. Train position P changes as train velocity V. Train velocity V changes as acceleration, which has several components. A sub L is locomotive traction. A sub A is deceleration because of the air brakes. A sub S is the acceleration under gravity due to the slope of the track. A sub R is rolling resistance, also called Davis resistance. The train experiences more of this deceleration the faster it rolls down the track because of a linear and a quadratic dependence on velocity. A sub C is the extra resistance a train experiences as it is going along a curve in the track. Finally, air pressure braking effect ramps up at rate m sub v as pressure propagates down pipes along the length of the train until it reaches a maximum, a sub v max. Now, I'll talk about how we dealt with effects that were unknown at proof time, the exact slope and curvature of the track. When designing the controller, we need to predict a provable upper bound on position p after one control cycle. And to derive this bound, we require a bound on velocity. In order to bound velocity, we need to deal with these unknown functions, the effect of slope and of curve. Fortunately, we know the worst case bounds on slope and curve. A given railroad will know its steepest slope, m sub s, and sharpest bend. So conservatively, we substitute in the worst case values to compute a bound on the dynamics. We use other information about the track to get even better worst case bounds to substitute in. For example, because slope change is only gradual, we use the maximum rate of change of slope to get a bound on its effect. Over here, you can see that I have a naive bound in the worst case, that's the worst case slope effect, m sub s, but also a more sophisticated bound from knowledge of the rate of change of slope. I will now highlight some of the other generalizable design and proof techniques we used in the paper. The first is a method to resolve circular dependencies. While designing the controller, we need to predict provable bounds on the variables of motion, but often these variables depend on each other. For example, in order to predict how large velocity will get, I want to know know the slope of the track, to know how gravity will affect velocity. But in order to know the slope of the track, I need to know how large velocity will get, so that I know how quickly slope is going to change. The solution is to bootstrap with a naive conservative value and then iteratively derive improved estimates. This controller design technique produces its own proof. Each iteration corresponds to a fixed number of proof steps. The second method is to use Taylor polynomials for approximation. Polynomial arithmetic is decidable, so Taylor polynomials can prove a useful approximation of complicated solutions. Finally, sometimes intermediate steps of reasoning, such as those that turn up in the case of circular dependencies, are themselves transcendental expressions. At these times, we represent them as extra ghost differential equations running alongside the real system and compare the original system to them. We evaluated our controller against a baseline from the literature by simulation. Here I present one of the train configurations from the literature that we simulated. The x-axis denotes train position in feet, while the y-axis has 3 rows. The first denotes velocity, the second shows acceleration, revealing when the train is braking, and the third denotes elevation, so this train is going through a trough. On the left, you see that the baseline undershoots the end of movement authority by over 2,000 feet. On the right, the verified controller limits undershoot to 502 feet. The reason the baseline controller is so conservative is that in order to compensate for the inaccuracies of numerical integration, it has to add a fudge factor, a safety offset. Suppose we were to remove the safety offset. Then the baseline controller becomes unsafe. The red highlighted region indicates where the train has a non-zero velocity, even past the end of movement authority. Our formally verified controller has eliminated the need for an offset and, as a consequence, is more efficient than the baseline. In summary, our work contributes a verified train controller that accounts for the full realistic FRA model. This is the first time a verified controller accounts for all the interacting forces of track slope, track curve, air brake propagation, and Davis resistance. We used several generalizable proof techniques, and evaluation shows that our controller is safe while being more efficient than previous work. This project was funded by the FRA. Our proofs are available online. Thank you.
Thank you, Aditi, for the interesting talk. We will go ahead and take some time for questions. You can just speak up, or you can also raise your hand, or you can type in the chat.
Oh, hello.
Hello.
Thank you for the talk. I might have missed a detail. I wonder if you could say something about the proof effort in terms of number of lines of formal proof and informal reasoning, if there is any.
So the number of lines of proof was over 180,000 proof steps. I think the exact number is on this slide. So the proof tactic was 2,545 lines long. However, if you run the proof in the theorem prover Chimera X, it will isolate more complex tactics for which we write a single word into like the under the hood, all of the underlying steps. And that was 180,000 something. So the proof effort, the proof tactic was about this long.
And compared to the number of lines of specification, what's the ratio?
The number of lines of specification is around, I think it's around 200 lines of code. So yeah, 1:10. And the informal reasoning was only in the design process. So the model was entirely proved formally.
Thank you.
Okay, any other questions? Oh, yeah, David, I saw you raise your hand.
Yes, thank you for an interesting talk. I was wondering a little bit about how you think about this kind of solution, how it can be used in practice, and also where the connection to a practical verified controller. So that you want to have this on a real train, and you want to be sure that it actually performs correct. What steps would be needed to be able to verify that the real system actually works as expected? I mean, there are many other aspects to a real system. So I was wondering a little bit if you can elaborate on that.
So the first step is to instantiate parameters correctly. So things like the resistance coefficient, the number of tracks, the number of axles, the weight of the train, and so on. After that, you probably want to run some validation on a real train. But I think that one of the big steps theoretically is taking this real valued proof to machine numbers. And the Chimera X ecosystem has a tool for this. Verify, a tool created by Rose Borer, is this verified automated pipeline that takes these real valued DL proofs to machine arithmetic in a verified way, preserving the safety properties.
Okay, thank you.
Okay, great. I think we can take one last question. If there is any.
I wonder, are you thinking of other applications? Are there parts of your proof that you could adapt directly to treat things other than trains, but similar dynamic systems?
So I think that going from trains to cars and planes is a question of dimension. And a lot of the features of this proof are generalizable. So if you look at the slide of general proof techniques, or actually the summary slide, let me just go there. Oops. Yes. So dealing with unknown functions, this is something you're going to have to deal with planes, with cars, because slope remains constant in a car. With planes, you need to deal with the currents in the air, circular dependencies. This is also something that's going to turn up in any system you deal with, where you're going to have some functions that depend on your position. Like in a plane, this might just again be the air currents. in a car, this could be like how fast you're allowed to go depends on the position you're at in the roadmap of the city. Taylor polynomials, like you can expect real systems to have unpleasant solutions, exact solutions that you want to be able to soundly approximate. So I feel like a lot of the techniques we used here to overcome the difficulties in verifying train dynamics are going to be necessary to model other real systems.
Okay. Thank you again, Aditi. And we can move on to, we can go back to our first speaker. Clara, could you try sharing your screen and unmuting yourself?
Yes, I should be unmuted now. Can you hear me okay?
Yeah, we can hear
Good.
you. Yeah.
And can you see my slides?
Yeah, great.
Excellent.
Okay, yeah.
So hello everyone, my name is Clara Hobbs, and I'm here today to talk about our work titled Safety Analysis of Embedded Controllers Under Implementation Platform Timing Uncertainties. As we all know, processor architectures today are becoming increasingly complex with moves towards multi-core systems, even in embedded applications. Additionally, the workloads that are being demanded of embedded controllers are growing larger and more heterogeneous. And these factors combine to make it so that increasingly it's becoming impossible to have safe and tight worst-case execution time estimates. So to avoid undue pessimism, many applications may work with measurement-based estimates that might not be the true worst case, which means that some deadline misses may occur in real systems. To view the effects of this on control systems, consider the example at right. This is a two-dimensional dynamical system with the state variables on the horizontal axes and time on the vertical axis. The nominal trajectory showing the controller operating as intended is shown in black, and a safety pipe is drawn around it in blue. Additionally, on this plot, there are 100 deviating trajectories resulting from deadline misses, where here we have a constraint that there can be at most 5 deadline misses consecutively. As you can see, the vast majority of these are shown in green, meaning that they don't leave the safety pipe, but 2 can be seen to leave the safety pipe at some time and cause a safety violation. This highlights one problem, that we can't prove safety simply by sampling, because just like you can't prove a deadline, you can't prove a worst case execution time just by sampling. You don't know when you've actually seen the worst case. To see the real world impacts of such a safety violation, well, in particular, the term that we use for this sort of change from the nominal trajectory is deviation. And this can cause safety violations in real systems. Consider an adaptive cruise control system. There might be some lane keeping controller, and in this case, deadline misses could cause incorrect steering inputs to be applied to the vehicle. This could cause the vehicle to swerve out of lane and possibly cause a collision, which of course is disastrous. So in order to prevent such collisions as the move towards autonomous vehicles occurs, we need to be able to compute safe bounds on deviation under timing uncertainties. So in this work, we focus on discrete linear dynamical systems of the typical state space form. We assume a uniform sampling period and the logical execution time paradigm. So the control input is applied with a 1 sampling period delay. And in particular, this allows us to use an augmented state space that contains both the state of the plant and the previous control input, so that we can then model these equations using a single matrix times vector operation, which we use in modeling the dynamics under deadline misses. So essentially what a deadline miss does, because it changes how the control input is applied, is it changes the matrix in that equation. And we can model the changes to that matrix using a finite state transducer automaton. For example, shown here, we see an automaton that allows a maximum of 3 consecutive deadline misses. And the matrices that are applied in this equation change depending on what transition is being taken. In order to be able to fill in what those matrices are, we need some strategy for how the control inputs are applied after a deadline miss. And in particular, because the software wasn't able to compute a new control input, that means that whatever strategy is applied has to be done in hardware. So simple strategies are the most likely to be seen in the real world. In this work, we consider 4 strategies. Others could certainly be envisioned. Each strategy combines one item from each of these 2 lists. So for the control input, we consider being able to hold the previous control input or apply 0 control input after a deadline miss. Similarly, for what we do with the job that missed its deadline, we consider the options of either killing the job immediately at its deadline or skipping the next job release and allowing the one that missed to finish. To give a concrete example of what such a strategy looks like, consider the hold and skip next strategy, which holds the previous control input on a deadline miss and allows the job that missed its deadline to complete. Now, in order to measure deviation, essentially all we have to do is, given the 2 reachable sets at a given time, compute the distance from them. So here we see the nominal trajectory in black again, with dots at the locations where it actually sits at a particular time step, and the reachable set from some sequence of deadline misses is shown in a blue rectangle. So essentially we need to compute the distance from a dot to a rectangle. And then we say that the deviation of any pair of runs is their maximum distance at any time step. So the overall goal in this paper is to compute the maximum deviation between the nominal run and any possible deviating run. And the problem with this that was alluded to earlier is that trying to determine this directly leads to a combinatorial explosion from the enormous number of possible deviating runs. So what we do instead is to compute a safe approximation to the maximum deviation by finding an upper bound. And in this work, we've developed 3 different algorithms for trying to approximate this. These are called the uncertain linear systems approach, the recurrence relation approach, and bounded runs iteration. In the uncertain linear systems approach, the idea is essentially to over-approximate all the different closed-loop dynamics that could occur in the automaton, rather than trying to approximate the different trajectories themselves. Essentially, you can think of each matrix as a point in an n by n dimensional vector space. And what this algorithm does is over-approximate all those matrices by an interval in that same space. And we can then use an efficient algorithm to compute all the reachable sets that are possible from any matrix in this interval, being multiplied by the state vector repeatedly. The second approach is to use recurrence relations, which essentially what these relations do is follow the transitions in the automaton for each time step and keep track of what states are reachable in each automaton location after each step. Then we take a box hull of all the reachable sets after a single time step and keep iterating this process until we reach the time horizon. Going further from this, we can consider that the main reason we have to do this approximation is that computing all runs for a large time horizon is infeasible. However, if we keep a very small horizon, say 3 steps, then it can be done efficiently because then we only need to compute 8 different trajectories. So a sort of natural extension of the previous method is the bounded runs iteration approach, where we, instead of taking single step reachability, simulate exact trajectories for a small number of time steps R, and then take a box hull of the reachable sets after every R time steps. Now, with 3 different algorithms to try, we implemented all of them. The first 2 we implemented in Python and the third in Julia. And we looked at 4 different case studies for evaluating these systems. There's a much more detailed evaluation in the paper than what I have time to present here. So if you're interested in seeing more about how these algorithms compare against each other, please see the paper. But to demonstrate the usage of these algorithms, we are going to consider the F1/10th steering model, which is essentially taking an F1/10th model car, which is for those of you who don't know, is a 10th scale autonomous driving competition. So
Sorry,
the controller.
Clara, to interrupt you, but the time is up. So could you wrap up your presentation?
Yes, certainly. So essentially, we can run this. We can run these algorithms on our different systems and compute deviation. In some cases, we might find that it's safe. In other cases, we might find that the maximum bound that we could have exceeds the safety pipe. And so the final takeaways, prior work examined the stability of control under timing uncertainty, but using our quantitative methods, we can evaluate safety properties instead, which enables a finer grained view of deadline mishandling strategies than has been possible before. And in the future, we plan to reduce the amount of over approximation using more advanced reachability methods and also consider statistical methods for estimating deviation. Thank you.
Thank you, Clara. Let's have Q&A now. I think we have time for 1 or 2 questions. Oh, yeah, Claire, please go ahead.
Yes, thanks for the presentation. I have a question about the fact that you have implemented a tool. Why didn't you use existing tools that can compute for you this reachability interval? Because there are tools from already closed loop systems.
Essentially, we did this ourselves because the exact properties required of such a reachability tool, we didn't find one from the literature that would be able to apply directly. If such tools exist, then I would love to hear more about them.
Okay, because I'm not sure I get all the details because the presentation was short and I quickly go through the paper, but it is based on matrix and automata. That's correct?
Mm-hmm. Mm-hmm.
Okay. I will send you some pointers maybe.
All right, thank you. I'd appreciate it.
Thanks.
Okay, thank you. I think we're running behind a little bit, so I think we need to wrap up Q&A here. Thank you again, Clara.
Thank you.
And we'll move on to our third speaker, Qiao Xie. Qiao is a PhD candidate in the Department of Computer Science at University of Illinois at Urbana-Champaign. His main research area is within programming languages, formal methods, and software engineering. Qiao will be presenting his work on verifying controllers with vision-based perception using safe approximate abstractions. Right, Qiao, please go ahead when you're ready.
Yes, hi. Everyone hear me okay? Yep.
Yes.
Yep. Okay. Hi, everyone. My name is Chao. I'm presenting our work, verifying controllers with vision-based perception using abstractions. This is a joint work with my colleagues at the University of Illinois at Urbana-Champaign. So our work proposed a method of certifying autonomous systems that uses deep learning enabled components. In particular, we're considering this vision, the neural network using vision for state estimation. And in this particular work, we studied the lane tracking system. As you can see that this car will use the front camera image to estimate the lane and trying to track the lane. So there has been quite some work in certifying, in checking the local robustness for each of the DNN. For example, there is this neural network verification competition has been going on for 3 years. But we found that there's only a handful of papers for verifying system level analysis with the neural network, and only very few of them are working on these neural networks for vision and perception. To verify such a system is very difficult for 2 reasons. First is that the DNN component, it is very hard to formally specify the input-output behavior for this deep neural network component because it requires reasoning with the pixel value. The second problem is obvious, that because of the image input domain is very high dimensional. So our work is based on 2 realizations, very simple realization on how to address these challenges. The first realization is that although we don't really know how to specify the component level specification for the deep neural network, we know for the system, the specification is clear that we want the car to track the lane center and stay within the lane boundaries. So if we can ignore right now, we ignore the perception and the camera sensor and assume that the system can work with the perfect position information, then we know there are plenty of formal verification techniques in textbook to prove the invariance of the car. But now, if we go back to the system with the DNN components, then the idea is that if we can relate this input ground truth state information with the output perception output, then we could deploy existing proof techniques. Therefore, our insight is to trying to approximate the camera and the DNN components together. So this would help us bypass the 2 challenges. First, the combined components now is performing a state estimation task, which is to use the ground truth information to get some estimated information. And this specification is naturally formalized with respect to the ground truth state. And the second it also avoid the second challenge because now the input and output domain for this combined component is much less dimensional than the image domain. So the contribution of this work is as follows. First, we take the control and the dynamics of the system, and then we take the known invariance for the system, and then we sample from the perception components, and we will output first. We can provide the safety assurance of the end-to-end system by approximating the DN plus the camera. Second, we derive this formal DNN approximation against the ground truth, and we coined this term approximate abstract perception in our paper. Finally, we also use simulation testing and to empirically measure the precision of our approximation with respect to the actual perception pipeline. So in this paper, we want to find this particular template of approximation as follows. So if we consider the perception pipeline as a high-level sensor, and we compare with a traditional sensor such as a GPS sensor, we know that it is similar that the GPS sensor is taking some unknown true position, and then providing some estimated mean value and the computed error bound to represent a possible set of estimated positions. So this particular approximation is a set value output function. So in this work, we are also looking at this shape or this template of approximation, but with more complicated setup. So now I'm going to dive into the details of our approach. We first need to formally define the state domain and the perception domain for the land tracking system. So the state is simple. It is the 2D XY position and a orientation of car with respect to some world coordinate. Now the perception domain is the relative distance and the relative heading angle with respect to the center of the lane. So for example, if we know at this setting the lane is exactly aligned with the x-axis of the world coordinates, then the relative heading angle is exactly the negation of the orientation with respect to the world coordinate. Now, if we consider the plot on the perception domain, dm psi, then each point on this dm psi actually represents one of this car configuration, and we represent the ground truth with the blue dots here. Now, even given one ground truth, the perception pipeline would give you an estimate output. And even under the same ground truth configuration, because of other environmental variations, there can be different front camera image, and therefore the perception can give you different estimation. Now, our approach are two steps. The first step is trying to find this estimate mean center. We apply linear regression on the data to find this estimate mean. Then the second step is, what is a reasonable circle around the mean center for represented set value? And the idea is that it should preserve the system invariance I mentioned before. And in order to preserve this system invariance, we consider this unsafe perception region where each of these unsafe percept will lead to wrong counteraction and in turn violate the invariance. We encourage the audience to read our paper to see the proof and the encoding into constraint optimization problem. Now, we also partition the state space and then learn a set value approximation for each of the state space. And the aggregated result then is a piecewise set value output function M. And in our paper, we proved that if we replace the actual perception pipeline with this approximation, piecewise approximation, this approximated system denoted as headsys with M will preserve the system invariance. Now, we also provide a measure to compare how close this approximation is with respect to the actual perception pipeline. We can calculate this precision score by just counting how many of the orange dots, which are the samples from the actual pipeline, to the how many of them are falling inside our approximation denoted by this purple circle. And then for each of the partition, we can map to a cell in this precision heat map, and with the darker green representing a higher precision score. Now, using this precision score, then we can investigate where DNN components can or cannot preserve the system invariance. So in this case, we show in this slides, I show 3 different precision heat map that is using increasingly finer partitions. And then we can observe that there are some common white regions, for example, on the top right corner. So if we map this top right corner back to the configuration of the car, we can see that the car is actually at the position where it's closer to the lane boundary, and then it is facing towards the lane boundary. So in this case, the car is already in a very nearly unsafe state, and therefore the approximation would require you to be very restricted so that the actual perception is not able to satisfy, the actual position would have problem to remain safe and satisfy the system invariance. We encourage audience to read into our paper about the experiment setup and a more comprehensive discussion in the paper. To summarize, we provide a method for end-to-end assurance of the autonomous system with a particle-sized DNA perception. And this is relying on our idea of using ground truth-based approximation for the DNA perception. And in our paper, we also provide how this approximation can be connected to the simulation testing, level analysis, and more comprehensive experiments. Now, this work suggests some more future research directions that to explore, for example, other intelligible structures such as decision trees, smaller neural networks, or adaptive partitioning. It would also be interesting to infer this system invariance while we are constructing these approximations. So this concludes my talk. Thank you.
Thank you, Chia. Let's take maybe one question from the audience. Okay, Parasara, please go ahead. Oh, sorry, I also saw Claire raised your hand. Sorry.
So I have a question, which is, do you generate the uncertainty in the state estimation? Is that for a given time step or throughout the entire trajectory?
Can you repeat the first part of your question?
So the uncertainty around the perception or the state estimation that you use for the neural network, is it for a given time step or is it throughout the entire trajectory?
In this work, the DNN is, we consider it as a pure function. So you are getting for each frame of image, you can consider.
I see.
Yeah.
I see. Thanks.
Okay, Claire, please go ahead. Maybe this would be the last question.
Okay, thanks. Thanks, Evictor. Just a question. How do you ensure that what's the output of a CNN is safe compared to the position of your vehicle with respect to the line? This part I didn't get.
Right. So yes, I skipped through that. I believe you are referring to how do we define this unsafe perception region with respect to the system invariance. I can give you the high-level idea is that we need the model of the dynamics and the controller, and then model it in constraint solver, or like in our case, we use the constraint optimization solver, and that. Given that, then the only unclear part, the unknown part, is the perception, and that we can symbolically define what is the unsafe perception, and we find this radius that minimize the distance so that it doesn't touch this unsafe perception region. The details is in the paper, and I also attend the poster. I'll be happy to answer more questions offline.
Okay, thanks.
Okay, thank you again, Xiao. We'll move on to our final speaker, Weidong Zhu. Weidong, please go ahead and share your screen. Weidong is a PhD student at the University of Florida. His research mainly focuses on system security, including security and storage, software debugging, and side channel attacks. Weidong is going to talk about NASA, non-volatile memory assisted secure deletion for flash memory. Okay, Weidong, please begin whenever you're ready.
Yeah, thank you. So can you hear me?
Yes.
Okay, thank you. Hi, I'm Weidong Zhu. I'm a PhD student at the University of Florida, and I'm very glad to present our work NASA, which incorporates non-volatile memory into flash-based SSD for secure deletion. And this is a joint work with my advisor, Dr. Kevin Butler. So secure deletion is a simple but critical technology to ensure that deleted data is truly deleted on the storage. Moreover, secure deletion is required by laws and organizations. For example, U.S. Department of Defense requires secure deletion of hard drives and other storage devices. However, secure deletion can be an issue in the storage system. For example, in the figure, data can be deleted insecurely because the stale data still exists in the storage, and this can be incurred by the limitation of the storage medium, such as the flash memory. So for the storage, flash memory is one of the most popular storage medium because of its high performance. Moreover, data is accessed with page granularity, and data can only be erased with block size in flash memory. However, flash memory is not friendly for secure deletion because it not allows in-place update, and still data must perform block erasure for sanitization. Moreover, existing secure deletion method cannot solve the secure deletion issue in the flash storage. So emerging normative memories such as the Intel 3D X-Point in their obtained product, the new kind of storage medium that has higher endurance and lower latency than flash memory. For secure deletion problem, since NVM supports in-place update operation, it is friendly to secure deletion. However, none of existing works discuss how to use NVM to handle secure deletion issue. So for the secure deletion of flash memory, currently there are three types of secure deletion methods for flash memory. Encryption-based secure deletion is to encrypt data with different keys. So we only need to delete the key if we want to delete the data. This mechanism is very fast. However, it suffers from improper key management and bad crypto implementation. For example, we need to use random number generation to generate the key. However, a weak random number generator allows attacker to recover previous keys. Scrapping-based secure deletion is to use scrapping operation within the flash memory. Since data writing is to convert flash storage cell from 1 to 0, so scrapping is to zeroize all the data bits so that the data is deleted. However, this property incur disturbance to increase the data error rate of the normal I request, and moreover, the scrap data can be recovered, and this already been proved by previous works. So scrapping-based secure deletion is not secure. And lastly, erasure-based secure deletion is secure enough because data erasure is an analog operation, and thus data cannot be recovered once it is erased. However, erasure will lead to high performance overhead. So this method is not feasible for flash memory. Therefore, the takeaway is that no method can provide strong secure deletion guarantee without significant performance degradation. So as I just mentioned before, that NVM supports in-place update operation, so it is ideal for secure deletion. However, NVM is too expensive for now, and its capacity is lower than flash memory. So currently, NVM is mainly used as a cache for flash memory. So our work will combine NVM with flash memory for secure deletion issue. So in our work NASA, firstly, we select the hierarchy that NVM and flash memory are coexisted within a SSD. And this hierarchy is already being used by Intel at their Intel obtained H20 SSD. Then in the NASA, we mainly have 3 modules. First is the address translation. This module is responsible for allocating physical data address to the logical data address in the operating system and maintaining the mapping table between them. And for the hybrid Evictor, it leverages data hardness and recency of real-world workloads to perform data eviction when NVM is filled up. For the shock prefetching, it prefetches data from flash memory to the NVM when update happens to the data to a data page in the flash in a flash block based on the spatial locality and hardness of the real-world workloads. So NASA mainly has the following process to handle write requests. First, if the coming writing data has no prior data existed, it will be deemed as no deletion happens, and it will be written to the NVM. Then if there's no prior data, we need to determine the place of the stale data. If stale data resides in the NVM, we directly perform in-place update to override the stale data. Otherwise, we write the new data into the NVM, and then we perform shock prefetching operation to erase the corresponding and perform prefetching operations, and then erase the corresponding flash blocks. For the hybrid Evictor, we divide the NVM storage space to different segments, which has the same size as a flash block. Then when eviction needs to be initiated, we firstly confirm data page that need to be evicted from the NVM to the flash memory by selecting segments with the smallest hardness value. Since we create a segment recency buffer to indicate the access recency of the segment, if the selected segment selected segment exists in the buffer, we should skip the eviction of this segment. Once we collect enough segments for eviction, we will start parallel eviction. The basic idea of parallel eviction is to select segments based on the parallelism of flash memory, and then we evict data with segment sequence, but to fully leverage the bandwidth of the flash memory. For example, page 0 will be first written to the block 0. And then we evict page 2 to block 1 instead of writing page 1 to block 0. Therefore, as you can see from the figure of the physical layout, our parallel eviction could maximize the throughput of flash memory without losing the spatial locality of data in a flash block. When an update happens to a data page in a flash block, we leverage shock to prefetch data page to the NVM for future potential access. First, in the block that update happens, we firstly find data page with high hardness value. Then we traverse the data page in the block to identify the page based on the spatial locality judgment by assessing their address distance. In the end, we prefetch those data pages to the NVM and perform block erasure operation to the selected block. Here I will talk about our evaluation. We use FEMU to implement NASA, and FEMU is an SSD emulator that can accurately simulate the latency of the flash memory. Furthermore, we build a NVM emulator built on FEMU that can emulate the internal structure of NVM device. Then we build a FIFO and LRU as comparison. Moreover, we implement scribing-based and erasure-based secure deletion to compare against NASA. In our evaluation, we may have 3 goals. First, we need to demonstrate whether the stale data exists in the caching systems. Then we want to know how efficient NASA is. Finally, we also need to understand the lifetime of the flash memory. So we test NASA with LRU and FIFO with FIO benchmark, MSR workloads, and SysTor workloads. Based on our experiment, stale data are inevitably generated in the caching system, and the percentage of stale data under LRU and FIFO caching policies are 9.5% and 18.9% respectively. For the performance, NASA will increase the average response time over LRU by 0.01% and decrease the response time over FIFO by 2.1% on average.
Oh, sorry, wait, but time is up. Could you wrap up your presentation?
Okay. And compared with the existing securitization, NASA can significantly improve the performance over those methods. And also for the lifetime, NASA can greatly improve the lifetime over erasure-based operation, erasure-based securitization. However, NASA is not good as the scribing-based strategy. However, scribing-based secure deletion cannot provide a secure deletion guarantee like the erasure-based operations. So existing secure deletion schemes are not, so to conclude our paper, existing secure deletion schemes are not secure enough for satisfying the requirement of data protection. NASA combines flash memory and NVM to achieve a strong secure deletion guarantee without significant performance degradation. In the end, we evaluate NASA with existing caching policies and secure deletion methods to demonstrate its efficiency. And thank you, and I'm very happy to answer your questions.
Okay, thank you, Wei-Dong. But unfortunately, I think we don't have time for the questions right now. But just as a reminder, the poster sessions will be taking place at the Bund after this session. So I would like to invite everyone to the poster session to continue with additional Q&A with the authors. Thank you again, everyone, for joining us today, and we will see you next time.
Cool. I think that we have to move